Hello guys, welcome back to my channel again. I know it's been a while, but I started something in the last two videos. I started the UK University Integration B Round 1 and the last part's remaining. So let's do those 10 questions. We've done questions 1 through 10, 11 through 20, and now the last lap from 21 to 30. Let's get started. So question 21 is integral from 1 2024 e to the x to the x divided by 1 over x, 1 over x, 2 over x, 3 over x, 5 over x, 8 over x, and so on, dx. Now, this was actually one of the easiest questions on the entire round 1 because the numerator has e to the x, of course, but the denominator is a Fibonacci sequence. You notice 1 plus 1 is 2, 2 plus 1 is 3, 3 plus 2 is 5, 5 plus 3, and so on. And the denominator actually is infinite. It dominates e to the x because there's no end to this thing. So when the denominator blows up, the entire thing will go to 0. That's it. That was the entire argument because it's an infinite denominator. That's all the argument. Okay, so moving on to a more serious question now. Question 22. Integral a to b tan inverse of x over a plus tan inverse of x over b divided by x dx, where we're given that a and b are both greater than 0. Now what you could do here is you could use Feynman method, differentiation under integration, but I guess a nice way of doing this is setting y to be ab over x. What that does, we have the integral. The upper and lower bounds will be the same because we get a minus from the differential and that flips the upper and lower bounds nicely. We have tan inverse b over y plus tan inverse a over y. All of that divided by y dy. And then we add both these integrals together, the one before and the one after. We can change the y back to an x because it's a definite integral. So we have inverse tan x over a tan inverse a over x tan inverse x over b. And I really need that extra space. Plus tan inverse b over x over x. I know that looks shabby. And we have a dx, of course. The main thing to notice is we can use the formula tan inverse x plus tan inverse 1 over x is pi over 2 for x greater than 0. So with that, we have 2i is pi over 2, and then we have two of them, so we have a pi a to b dx over x, which is pi times ln b minus pi ln a, which is pi ln b over n, and then we divide by the 2. Pi over 2 ln b over a. That's the answer. You might use some sort of Frullani's theorem for this, but this is one way of doing it nicely. Question 23. So, integral 0 to infinity sine of x sine 2x divided by x dx. First of all, I see a product of sines or cosines. My eyes light up. I want to use the product to sum formula. So this becomes cosine of 2x minus x, which is x, minus cosine of x plus 2x, which is 3x, divided by x dx. And now I'm going to use a really nice, very nice property. So remember, maybe I use a different color, that integral 0 to infinity f of x g of x dx equals integral 0 to infinity Laplace transform of f of x times the inverse Laplace of g of x dx. This is a very, very powerful property, and I haven't used it in a while, but I'm going to use it because notice the Laplace transform cosine of at as a function of s is s over s squared plus a squared, and the inverse Laplace of 1 over x as a function of, I don't know, t or something, doesn't matter, is just 1. So I'm going to use that on the two integrals I have here. One integral, which is this, and then minus the other integral. So I'm going to use it twice on two integrals. So I get I is 1/2 integral 0 to infinity x over x squared plus 1 minus x over x squared plus 3 squared, which is 9 dx. What's wonderful about both of them is we can integrate them directly. That's 1/2 times 1/2, 1/4 natural log of x squared plus 1 minus natural log of x squared plus 9, which I can divide it out in the argument like that, from 0 to infinity. Now at infinity, we have 1, and at 0, we have 1/9. So we can simplify all this. 1/9, we can absorb the minus, get a natural log of 9. So 1/2 natural log of 9, which is 2 times natural log of 3. It's 1/2 ln 3. That's it. That's the answer. That's a very quick way of doing it. You could have probably used some sort of forced Frullani at this point by inserting an exponential function. So basically parameterizing the family by introducing an exponential to force Frullani. Because for Frullani, you need the horizontal asymptote. And yeah, you could have done that. That totally works. But I thought we haven't used this property in a while, so I'll use it, and it elegantly solves the question for us. Now moving on, we have this requires more symmetry now. I hope I didn't miss, yes, 24. Integral from -1 to 1, natural log of 1 plus x times 1 plus x squared, 1 plus x to the fourth, so on to even powers, 1 plus x to the 2024 divided by x dx. Now, if you notice the pattern, everywhere we have an even power except the first term. And that is exactly what we're going to exploit being on this symmetric interval. So x goes to minus x. That gives us integral minus 1 to 1. We have a negative sign from the imbalance between the dx and the x. So we have a minus ln. Now we have 1 minus x. The rest, the other even powers are not affected. Just the first term gets a 1 minus x. Divided by x dx. So the minus sign from the dx is gone to fix the integrals, but there's one extra minus sign from the denominator, which is the imbalance minus. We can add both of them together. So notice the terms that are in common will cancel each other. So we have ln of 1 plus x minus ln 1 minus x divided by x dx. And now we can actually write the second integral nicely. We can do x goes to minus x again, just on the second integral. So we get 2i is 2 times minus 1 to 1 ln 1 plus x divided by x dx. That's nice. Now I just becomes, we can expand the natural log as this infinite series minus 1 to 1 x to the n minus 1 over n dx, which will end up giving us n equals 1 to infinity. Plugging in the bounds, minus 1 over n squared minus 1 to the n divided by n squared. And we can actually rewrite this nicely as 2 times sum from n equals 1 to infinity, or rather 0 if you want to start the sum that way, 1 over 2n plus 1 squared. It's just the sum of odd terms, which we can write sum from n equals 1 to infinity 1 over n squared minus 1/4 sum equals 1 to infinity 1 over n squared. So I'm writing the square of the inverse square of odd terms as all the terms, inverse square of all terms minus the even ones, but the even ones had a 2n, the whole squared, which was a 4. I took that out. And that's 2 times pi squared over 6 minus pi squared over 24, which is pi squared over 4, which is just the Dirichlet eta function. So that's nice. We've solved this problem. There was a lot of writing individually each term of the series down to give us this general form, and then we can break the inverse square of all terms as inverse square of all terms minus the inverse square of even terms. We pull the 2 out that each even term has to give us a 4. That's all we've done here, and then we just simplify using the Riemann zeta. Okay, moving on to the next question. Actually, this was the question that I think many people struggled with. Although it looks kind of tame, it's sort of obvious what property we need, but integral 0 to 1 sine pi x natural log of the gamma of x dx. So we can use the King's property again. So we have pi minus pi x. So what I've done is x goes to 1 minus x. That's the King's property. ln gamma of 1 minus x dx. And I can rewrite this using some properties of the trigonometric functions as sine pi x again. No minus sign, nothing. Ln gamma of 1 minus x. Nothing over there either. But now we add both of them together. So when we add them, we will have to multiply in the products, in the arguments of the natural log. Sine of pi x. We have natural log gamma of x, gamma of 1 minus x dx. And now we use the famous reflection formula for the gamma function to give us sine pi x as it is, and ln pi over sine pi x dx. Now that's nice. From this we get natural log of pi integral 0 to 1 sine pi x dx minus integral 0 to 1 sine pi x ln sine pi x dx. I should probably make some space for that. Okay. Now the first integral can be evaluated nicely, and I'm not going to do it. It's an elementary integral. 2 ln pi over pi. So all you do is this becomes a minus cosine pi x divided by pi by the inverse chain rule, and then plug in 0 and 1, and you get the 2 over pi minus 1 over pi, because what I'm doing here is u equals to pi x. So I get the 1 over pi integral 0 to 1. Sorry, 0 to pi now with this new change of variables. Sine of u ln sine of u du. And we use integration by parts on the second guy basically. So we get 2 ln pi over pi minus 1 over pi. The minus cosine from the antiderivative of the sine, ln sine u as it is, 0 to pi, plus integral 0 to pi. We will have the cosine, 2 cosines from differentiating the natural log, and 1 over sine. Because when we differentiate this natural log, we get a 1 over sine and then a cosine in the numerator. That with this cosine will give us cosine squared divided by sine u. And that's good. We can simplify the first guy nicely. We get 2 ln pi over pi plus 1 over pi, and then cosine of pi is minus 1, sine of pi is 0, so we'll have to take care of that case. Same with the one in the 0. But let's just keep that term for now. So it's going to be minus cosine u ln sine u 0 to pi, and then we can simplify this. Cosine is 1 minus sine squared u over sine u du, 2 ln pi over pi minus 1 over pi cosine u ln sine u 0 to pi. The second integral, you have a sine squared over sine with a minus. That becomes a positive cosine, which can be evaluated. But the problem is this other term, which is the cosecant. 1 over sine is a cosecant u, which we know evaluates to is natural log cosecant u minus cotangent u in the antiderivative, 0 to pi. So the cosine term is no problem at all. It will give us a minus 2. With this minus will give us a plus. 2 ln pi plus 2 all over pi. But the problem is these other terms, right? So we have minus 1 over pi. We can rewrite all of this. Natural log of cosecant u. I can combine the natural logs. Minus cotangent u divided by sine of u to the cosine of u. Because we had a cosine u times the ln sine. So we can take the cosine, raise sine to the power of the cosine, and then combine them under the logs. So we get this big log. And you'll see why I'm doing, because individually they're in an indeterminate form. Together they stand a chance of getting evaluated to something. But we can simplify them even further before we do such an evaluation. We can write this as cosecant is 1 minus sine. So we can take the sine power down, and cot is cosine over sine. So we have a combined uh, sine of u, which I can write using the properties of exponents is 1 plus cosine u 0 to pi. Now let's do the limits. So at limit as u goes to 0 of this thing here, taking the limit inside the natural log function. So when I do that, well, we can expand the cosine with its Taylor series. So cosine of u is 1 minus u squared over 2. So we'll just have a u squared over 2 divided by, in the small limit, sine of u is approximately u as u goes to 0. And cosine, if we expand it according to the series, we get a 2, because the first term of the cosine Taylor series is the 1. So we get 2, and then we have a u down there, so we have a u squared. And in the limit u goes to 0, this is just 1/2. Similarly, when we have the limit that u goes to pi, 1 minus cosine u over sine of u, 1 plus cosine u. We can do a change of variables here. U goes to pi minus u, and what that does is just introduce a minus. We get limit as u goes to 0, but that changes the minus for the cosine to a plus, and a plus to a minus in the power of the denominator. With a similar analysis as before, we get that we have a 2 in the numerator from the Taylor series expansion, and we have u to the u squared over 2, but then u is going to 0. So this is sine u to the u squared over 2, but u is going to 0, and that will dominate. The power will always dominate. So we get something to the power 1, which is 1. In the limit u goes to 0, doesn't matter. We just get 2. So we have 1/2 one side, we get 2 the other side. So in the limit, when we evaluate all of that, we get ln2 minus ln 1/2, which is 2 ln2 with a minus. So in the end, we have, I should use a different color. 2i is 2 ln pi plus 2 minus 2 ln2 from the limit evaluation over pi. So I is ln pi minus plus 1 minus ln 2 divided by pi. If any of this part's not clear, please send me an email. I've tried to go through it as in detail as I can, given the time constraint we have. But it's all asymptotics. If you trust the limiting process, it works out nicely. The next question was very interesting. Probably one of those few that we haven't done on this channel. We have to find the max where k belongs to the reals. Integral 0 to sine squared k sine inverse square root x dx plus 0 cosine squared k cosine inverse square root x dx. Fair enough. Maybe we want to move this down a little bit. Okay, and to solve this, these problems define f of k to be, whatever we had on top there. So because we have to find a max, we have to set the derivative to 0. Sine inverse square root x dx plus cosine squared k cosine inverse square root x dx. So when we take the derivative f prime of k, we get sine inverse absolute value of sine k, because square root of square will give us the absolute value, to be precise, and then the derivative of the upper bound, which is 2 sine k cosine k. Similarly for the cosine, but we have a minus from the derivative. Cosine inverse absolute value cosine k 2 sine k cosine k. Now recall that sine inverse absolute value sine k equals cosine inverse absolute value cosine k to, well, just be k. So f prime of k is 0 for all k belonging to the real numbers. So that means its value is essentially fixed for all k. So it's a constant for all k. So we can just pick any k that's convenient to us, and that should be the max, because for a constant function, its value at any given time is, well, the max. So pick k equals pi over 2, because f of pi over 4 is 1/2 and 1/2 in both integrals, and that's nice that we can evaluate that nicely. Plus 0 to 1/2 cosine inverse square root x dx, because we can use the nice inverse trigonometric properties to give us a pi over 2 when we add them under the common integration. And that gives us pi over 4. That's perfect. We've solved that one. There's many ways of doing this, of reasoning. This is probably the most effective one. Question 27. Integral 0 to infinity e to the minus x over square root x, xth power of e dx. When you see a square root like this, set that to u usually, and that works out. Dx is 2u du. 0 to infinity, we have a 2. E to the minus u squared, e to the minus 1 over u squared du. And we can complete the square. So define, let's take white again, j to be integral 0 to infinity e to the minus u minus 1 over u squared minus 2 du, which is basically this integral in blue with the squares in the power completed. So we set u to 1 over u, and we get 0 to infinity e to the minus u minus 1 over u squared minus 2. We have 1 over u squared du. So we add both of them up. 2j is integral 0 to infinity e to the minus u minus 1 over u whole squared minus 2. 1 plus 1 over u squared du. And this is nice because if we set this to some variable y, this is dy. So y is u minus 1 over u, so dy is 1 plus 1 over u squared. So 2j is integral minus infinity to infinity e to the minus y squared minus 2 dy, which is nice to evaluate, square root pi over e squared, the Gaussian integral with the e squared factor. But if you remember, 2j was just I. So 2j was just I. And there we go. We've solved our problem. Moving on. Question 28. We have integral 0 to 1 sine inverse x squared sine inverse square root x divided by square root 1 minus x squared dx. So let's split them up. Let's divide and conquer. Dx plus 0 to 1 sine inverse square root x over 1 minus x squared dx. So in the first integral, we basically just keep it as it is. We work on the second one, u equals square root x. So I'm just gonna write the first one because we're gonna need that later. When I use that substitution, I get sine inverse u over square root 1 minus u to the 4th 2u du. And notice we can actually rewrite this slightly to put it into a more agreeable form. So we have sine inverse of u 1 minus u squared squared 2u du. Now again, the clever observation is to notice the 2u divided by square root 1 minus u squared squared is actually the the derivative of the arc sine of u squared. So maybe I can circle this around and say that's the derivative of sine inverse of u squared. So we have a nice setup for a integration by parts problem. But I'm still not touching this first term. 1 minus x squared. So the when we do the antiderivative sine inverse of u squared, sine inverse of u from 0 to 1 minus integration 0 to 1 sine inverse of u squared, and the derivative of that is 1 minus u squared du. So you notice that cancels nicely with this. We're just left with sine inverse u squared sine inverse u 0 to 1, and both of them give us pi over 2, so we have pi squared over 4. And that's it. That's how we solve 28. And then comes the grandmaster question of all of them, 29, which was probably very difficult, very difficult to solve given the time that we had. So 1 over ln 2 to the 2024, limit n goes to infinity, sum k equals 1 to n, nth root of 2 to the kx, kx to the fourth over n kx cubed plus 1 dx. First of all, we can rewrite this a little better. You can have x 2 to the kx over n over n plus, so I've multiplied and divided by x cubed in the numerator and denominator, k x cubed. Yeah, I've divided by k as well, dx. Now notice this chain of inequalities, and I think this was the hardest observation. Sum n equals 1 to infinity, sorry, n 1 to n, 2 to the k over n x over n plus 1 over kx cubed, which was our original limit sum, less than or equal to limit n equals goes to infinity, sum, I think this was a k, one to n, and 2 to the k over n times x over n. This is totally fine because n is less than this term here, and therefore the fraction is greater. And this is actually just the Riemann sum, 0 to x, 2 to the u du. And also notice that limit n goes to infinity, sum from k to 1 to n, 2 to the k over nx over n plus 1 over kx cubed is also has a lower bound. Limit n goes to infinity, sum k equals 1 to n, 2 to the k over n x, sorry, there should have been an x here from the previous step, over n plus 1, which is greater than or equal to limit n goes to infinity, n over n plus 1, So we multiply and divide by the n. Two to the k over n times x over n. Now in the limit, this term goes to 1. And this is again the Riemann sum, integral 0 to x to u du. So the upper bound and the lower bound of this sum in question is bounded by this same Riemann sum. So therefore, by the squeeze theorem, it has to equal the Riemann sum. So we have integral 1 over ln 2 to the 2024. And then inside we found this to be a Riemann sum, 0 to x, 2 to the u, du, dx. This turns out to be 1 over ln 2, 1 over ln 2 2024, 2 to the x minus 1 dx, which can be simplified 1 over ln 2, 2 to the 2024 over ln 2 minus 2024 minus 2 to the 1 over ln 2 over ln 2 plus 1 over ln 2, 1 over ln 2, 2 to the 2024 minus e plus 1 over ln 2 minus 2024, where we've used the fact that 2 to the 1 over ln 2 is 2 to the ln e over ln 2, and we change the base to get 2 to the log base 2 of e, which is just e by definition. So that's where this e is coming from this factor. And that's the big answer to this question. Moving on to the last question, which also was a good question. Integral 0 to pi over 2 cosh inverse sine of x plus cosine of x dx, integral 0 to pi over 2 cosine inverse, and we have square root 2 from the cosine compound angle formula. We've used cosine x minus pi over 4 is 1 over square root 2 cosine x plus 1 over square root 2 sine x. So, and that's why we can do a change of variables here. So x minus pi over 4 goes to x. So we get integral from minus pi over 4 cosh inverse square root 2 cosine x dx. But using the fact that the cosh inverse is even, we have 2 times integral 0 to pi over 4 cosh inverse square root 2 cosine x dx. Now here's where we introduce a Feynman parameter, 0 to secant inverse of t cosh inverse t times cosine of x dx. You will see why this parameter choice is very good. Now notice one thing, the derivative of cosh inverse of x is something we're going to need when we do I prime, is going to be 1 over square root x squared plus 1. So I prime, as we usually do, it's going to be 0 to secant inverse of t. We have cosine of x divided by t squared cosine squared x plus 1 dx from the chain rule, plus the derivative of the upper argument. So cosh inverse t cosine secant inverse of t, and the derivative of the secant inverse with respect to t. That's the entire, the complete Leibniz rule. So this gives us integral 0 secant inverse of t cosine x divided by t squared cosine squared x plus 1 dx plus cosh inverse t times 1 over t, because cosine is 1 over secant. Secant and secant inverse cancel, so there's a t in the denominator. That gives us t times 1 over t, so that cancels. Cosh inverse of 1 is 0. So the derivative of the secant inverse doesn't matter, because cosh inverse of 1 is 0. So we just have integral 0 to secant inverse of t cosine x over t squared cosine squared x plus 1 dx. Substitution comes in, u equals t sine x, and du is t cosine x dx, but that's not the hard part. The hard part is evaluating the upper bound. So we have t sine of secant inverse of t for the upper bound on u. So that's t square root 1 minus cosine square secant inverse t, which is t times square root 1 minus 1 over t squared, which will just give me square root t squared minus 1. That's the upper bound. The lower bound simply 0. 0 square root t squared minus 1 du over t times square root t squared minus u squared minus 1. We can pull the t out, 1 over t. And then we have du over square root of t squared minus 1 minus u squared. Now remember this nice formula we have, that the integral du over square root a squared minus u squared is sine inverse u over a plus c. And we have the same thing here. We have a, instead of a squared, we have t squared minus 1. So this just becomes sine inverse u over square root t squared minus 1 from 0 to t squared minus 1. At 0, that's 0. At t squared minus 1, it's 1. Sine inverse of 1. So that's pi over 2. 1 over t, and that's 0. This all is I prime of t, let me remind you. And so I of t is pi over 2 ln absolute value t plus c. I of 1 is, let's go back to the definition. I of 1 is a secant inverse of 1, so it has to be 0. Because then we will have 0 to 0. So that means our c is also 0, because natural log of 1 is 0. So I of t is pi over 2 ln absolute value t. But for our I was, we had pi over 4. So pi over 4 is secant inverse of root 2. So we have to plug in root 2 for t to solve the problem. So I is I of t equals square root 2. And that gives me pi over 2 ln square root 2. So that's and that was this was twice. We needed a factor of 2 there. So I is just 2 times of that because we had a 2 up there because of the symmetry. I have a 2, so that cancels. I get a 2 from the square root, ln 2. That's how we solve this problem. Apologize, I didn't notice we had a 2 in the beginning from the symmetry of the arc cosh function. And then we just work with the parameter and then we introduce a 2 because I of t equals square root 2 is 2 times I because of the 2. So that's where the 2 comes from, guys. Sorry for that. But that's all the questions I had to do, and that was all of round 1. Please like, share, and subscribe to my channel, guys. I work really hard for these videos, and I appreciate your patience. In the meantime, keep doing math, and peace out.